Okay, this should be pretty quick, like 5 minutes probably. Well, without discussion,
I think everything's 5 minutes. So we can try to avoid one.
Let's play with a simple diagram here.
Okay, so basically this is an alternative to using the 3D displacements that I used previously to match graphs. So before, in order to match graphs, I basically used the difference between the previous XYZ location and the current XYZ location. So the displacement between those 2 points in space. And that displacement is not rotation invariant, which means you can't recognize the object if it's rotated. And using this representation,
why wouldn't it be? Because I mean, in theory, if you rotate the object, you rotate the reference frame, and you're just saying if I don't know how I rotate it, it doesn't work. Or, I mean,
it's assuming a priori you don't know the reference.
Okay.
Yeah, if you don't know the reference frame.
Yeah, given that the displacement relative to the object's reference frame, you can't do it.
Yeah.
Okay, but if you calculate displacements independent of the object reference frame, you could. Okay.
Yeah. If you would have that knowledge, then that would also work. But yeah. Okay. I'm assuming that you don't know that.
Well, okay.
And with this, it would still work without knowing that reference frame.
Okay.
So let me just go over it real quick. So here that's what it says in the paper where they introduce it. So for 2 points, M1 and M2 with normals, N1 and N2, we set D, which is, I would say, the displacement that I previously used, equals M2 minus M1. And it defined the feature F as the length of this displacement, and then 3 angles. First angle is the angle between the normal of the first point and the displacement between the 2 points. So it's this angle here. I hope you can see my mouse. The second angle is the angle between the normal of the second point and this displacement between the 2 points. And the third angle is the angle between the 2 normals. And those 4 numbers basically denote the feature between those 2 points in space.
It's just my intuition thought said that the third angle is determined by the first 2 angles, but apparently not. So let me see if I understand that. The normal to the distance. D is just a linear distance. No, D is a what is D? D is a direction.
Yeah, D is basically the displacement, but for the feature we use the length of this displacement. So it's basically how far is point 1 from point 2. So the distance between the 2 points.
So then you're taking the angle between. Well, why do I care about the distance? I'm just trying to calculate an angle between the normal and D. I don't care what the length of D is, right?
Yeah, so basically, if you look at this picture here, the idea is that these 3 point pairs would all have a very similar feature attached to them, or they would have the same feature attached to them. But for example, if you move this bar a little bit up, so let's say you have this point and this point, the normals are still pretty much the same. So the angles would be pretty similar, but the distance would be different. So it would have a different feature.
Oh, I see.
I mean, one way to look at it is that if D is very small, you have a representation, given whatever the angle difference between the 2 normals is, of one curvature. But if D is very far apart, and you're not sampling anything in between, but the thing is that then the curvature would be less because you have a greater distance over which to swing that normal.
Yeah.
So
yeah.
Well, the bigger D is, the less knowledge you have about the shape beyond them, right? It's just as D gets smaller, then you sort of get, as D approaches 0, you approach the instantaneous curvature of the figure.
Yeah,
okay.
and
I think I get it. right?
Yeah, and if we would have a sensor that samples in equally spaced intervals, then D would always be the same, and we would just, it wouldn't be super informative. But if D can be different, like for example with saccades, that it can have a lot of information in it.
Well, if D was along the edge of the shape, then it would be very informative, right? I could say, because not a straight line D, but if I want sort of if I want every point was equally spaced along the curve, then D would vary a lot, and it would capture them.
Yeah. Yeah, right. Yeah. Okay, yes, so that's the basic idea, to use those 4 numbers to quantify instead of the displacement between 2 points. So basically that would be the attribute of the edge of a graph. And using that instead now solves the problem of detecting objects from new rotations. So on the left side, this is detecting 5 different objects rotated the same way that they were learned, and on the right, detecting them in a different rotation. And it's pretty much the same performance. So it works quite well. The bigger question would be if we can assume that we have knowledge about the point normals. So do we know essentially, how do you call it, perpendicular?
In the case where vision and touch seem to be very, very different, and with touch, you would know this in some sense, right? If you think, imagine your finger moving around the object, you inherently know where the surface is relative to your finger, right? In some sense, whatever patch of your skin is touching the object, it's going to be at a tangential point, and so you would know this, I think, with touch.
I guess if you know the local 3D curvature, then you have the normal.
Yeah.
But how? I mean, isn't this to determine the local 3D curvature? I mean,
Yeah, I think a touch sensor can pretty naturally determine it. And then the question would be if we could also determine this from a patch of vision of a vision sensor.
That's what I just talked about. Would that do?
Yeah,
You simply wouldn't need this. Wouldn't need these point features.
But could you use that to get this these normals? You were just talking earlier
About the curve, possibly.
Yeah, good.
I mean, that is a tricky thing in the vision sense, right?
So dependent on lighting.
Well, it depends on a ton of things, right? This is the weird thing about it, and it's clear how you could do this with touch. It's not clear how you could do it with vision.
Yeah, we might be able to learn this in vision.
And now, that we talked about that too. Like, what if you had touch as your ground truth, and then you're getting these visual inputs, and in different lighting conditions, there's weirdo stuff going on. Could you do it? I don't know.
Yeah, you could use your touch to train the vision.
Yeah, touch is so we could just say, assume we know this ground truth here. Could you train a vision system to imagine we have an object and we have ground truth, so we don't have to touch, we just have ground truth. Then we could say, given this visual input, could you actually learn these normals?
You could also use movement to train. Like once you have a ground truth, then you can move and see how it changes. Because as you move, how the angle changes, but the input will change.
Yeah.
But you could.
But still in a very complex way that's hard to imagine.
Right.
In a visual point.
If you have the point cloud, you can have the point normals. And the other work we discussed before, we assume we have the point cloud. So, but what's different in this?
Well,
A point cloud doesn't give you the normal.
No, you can't calculate.
You can count, you can approximate it, but if the points are really close together, then you get a good curvature. But just from a single point.
Well, I don't know. Maybe it's not too hard to do. I don't know.
Yeah, so I'm using a point cloud right now to get the normals.
Right. So I thought you said you were questioning how could we do this, but now you already have a way of doing it. So.
Well, that assumes that we have a point cloud which might not be the case if we're just moving a finger along the edges, then we only get one point at a time. We don't have the whole point cloud to estimate the curvature. So
it seems to me a finger moving along an edge is it just intuitively feels like, yeah, I know exactly what, I know the edges, I know its sharpness, I know its orientation. I can sometimes I'm sensing the normal, you know what I'm saying?
yes. So we should be able to get the normals from just one sensation instead of all the whole cloud of sensations.
I think it's also possible to cheat a little here if we want. I'm not sure if you can cheat. Like I ask myself when I'm actually touching something, is there really one column in my cortex that's active? Probably almost certainly not. I don't know if I can ever actually just get one column touching something, right? Because the column, the receptive on the sensory organ, they're overlapping. And so you touch something, you're going to have multiple columns getting input, and they have short-term connections between them. It's very possible that, you know, we were able to integrate several columns instantaneously to get more information. I don't know. My point is, it seems like I definitely have it. It's like I touch something, it's like I know what the curve. I know it's not just, oh, there's a dot. It's like, oh no, there's an edge and it's rounded and it's oriented this way, and I can feel all that.
Yeah. I was also thinking using multiple neighboring columns could solve a lot of these problems, like detecting the edges and the curvature.
Yeah. And again, right. And again, it's clear that we are able to do that. I mean, I'm conscious of it. I can tell you what the edge is and what the surface is. I just feel it, right? We all do. So it's clearly there. So we don't know exactly how it's done, but multiple columns could do it. You know, it's also in the cortex, the lower layers have a broader receptive field than the upper layers. So the lower layers would be looking at a larger part of the object, and the upper layers are looking at a smaller part of the object. And so one could argue the lower layers are now determining this curvature because they've got input over a broader area, but the upper area is determining the feature that you're going to put at some point. So, you know, there's lots of tricks like this, right? And so a single column actually is like multiple columns in the sense that it's detecting over a broader area. And then it's going to integrate that information. Then you can say, well, at that, it can determine curvature, and then you say, oh, well, at the point of the curvature, here's the feature. That kind of thing.
The thing about touch to me is you actually have two modalities simultaneously. I mean, the fact that your finger is impeded, it can't push beyond a certain point. You can just move your arm and your hand with your finger in contact with the thing, and you can trace out the course shape. But on the fingertip, then you have the fine detail of the texture and confirmation of the local curvature. So you're actually getting a multimodal input of space with touch.
Yeah, I was arguing the opposite. I was arguing that the curvature is detected by the broader input, and the feature, let's say the texture or something, is detected by the smaller input at the top. But it is.
I think they can confirm each other. You know,
maybe. I know that's true for vision. I don't know about touch actually, but it's probably true. I think it's a general property of cortex. Anyways, we can put that aside. We can just assume that we'll have some sensor that can, if you had a touch sensor, it could tell you this information. And I don't know about the visual world, how easy it is, but if you got a point cloud and it's working, then I guess it's working.
Yeah, so two more notes just in general. So even though those features are rotation invariant, we can still extract the pose of the object once we recognize the object, because the matching procedure basically narrows down where on the object we are. And once we know where on the object we are, and we know where in space this point is relative to us, we can calculate the pose of the object relative to us. That's one more side note. And the second one, I'm not sure, but it might make it easier to add more slack for the sampling problem, because if you just have the XYZ displacement, it's difficult to say do you want to have more slack in the X or the Z or the Y direction? Could the displacement be longer, or could it be more rotated? Well, here those factors are nicely separated out into 4 variables. So we can say we don't care so much about the length of the displacement matching exactly, or we don't care so much about the angle, it would be easier. And here's just one example of, so this model was stored in memory with 100 points from the surface, and then here that are 200 points from the surface with different features and connections between them. And it at least for a short time recognizes the mug and then thinks, okay, it's not anything, it's not any object that I know anymore. But that was just a quick test, but I feel like with those 4 variables, it could be easier to explicitly add slack in either like length of displacement or angles.
So it could be somewhat invariant to changes in scale, for example. If you have more slack on the displacements, you could have larger or smaller.
Yeah, I didn't even think about that. Yes, I think it might allow for scale if you allow explicitly only the distance factor to vary.
Yeah.
But it's funny because it seems like every time I think about that, oh, that'd be nice, but sometimes the scale varies in direction. What if I showed you a coffee cup that was, instead of being circular, was oval? And well, you see that, you get it right away, right? So that's not like, it's like, okay, it's stretched in one dimension, but not in the other dimension, but you immediately recognize it and you could immediately learn it. And it was like, so it's kind of weird. It's like it's not, I'm just pointing out that scale isn't just scale. Distortions occur in non-uniformly, and it's weird.
But I feel like with those distortions, it may be important to consider hierarchy and the features as well, because, for example, if you have a very distorted cup or like the Dali clock or something, if you'd only feel the morphology, you would probably not recognize it.
Why do you say that? Well, if it's highly irregular, yeah, but once I've learned it, I can very quickly learn one of these distortions, right?
Yeah.
I may not recognize it as a cup right away, but I could definitely learn this object, and I would then know that it's a cup, and I know I could put liquid in. I know I could grab the handle. I know how to drink out of it. It's all those other things that come along with it. I wouldn't say, oh, this is something completely new.
Yeah, but I mean, I was thinking about how much distortion can we tolerate. So here are 3 examples.
Oh, you put these up. I thought you didn't put them up.
And so for example, similar to what you said, Chef, right? If it's the rim is a little rotated, or if it's all tilted. But for example, the last one, if I rotate it this way, it doesn't feel like a cup anymore. It's more like a cartoon character.
Maybe.
The face, this could be a face.
I guess I'm saying, when we say how much can we tolerate, are these objects that I'm actually learning now, or like
Well, let's say you learned a coffee.
I write it up, and now I see this thing.
Yeah.
Yeah.
So sort of, yeah, there's
The question is what I label this as a cup. I would definitely see it as, I would see it as different yet somehow the same.
Right.
Right. Well, it seems like a pretty good technique in general, right, Viviane?
The point pair features.
Yeah.
Yeah, I like it. It's a very nice description of how 2 points in space relate to each other, I think.
Two planes relate to each other.
Yeah. 2 points with rotation attached to them, I guess, or yeah.
Two. I mean, they're normal to a plane, so there's really 2 planes.
Yeah.
Two tangential planes.
Yeah. So I think it has a lot of nice properties, and it solves some problems. Yeah, I just wasn't sure if we can assume that we can get those normals. That would be like the major difficulty with it, I think. But I feel like
it sounds like we can, right?
Yeah.
We can if we have the point cloud, but let's say we don't. You have a partial point cloud from a sequence of observations. If you can get the normals for the point cloud, you could train a network to also retrieve the normals from a partial point cloud. Wouldn't be like perfect, but at least you don't have the assumption of having the entire point cloud.
Yeah.
I mean, in some sense, it feels like either whether I'm touching something or looking at something, I'm gonna learn the shape of this thing. In some sense, I have to be able to determine these surface normals. How else could I do it? It seems like I can't think of any other way. It feels like I have to do that, and I am able to do that. I'm looking at this chair in front of me right here, and any point I look on this chair, I have a sense where the surfaces are and the edges are, and I can describe where the point cloud is on that. I can do it with one eye closed. So it seems that somehow that information is there. So we should be able to do it.
Yeah, it's also a variant that I presented like 2 weeks ago, which was instead of the normals, it was like 3 displacement vectors in sequence. And it's sort of a very similar way you get the angles between them. So instead of the normals, you get, so you use 2 displacement vectors to define your plane, and the other one is, and so yeah, you
don't need the normal in that case.
Yeah, you just need the displacement.
But I'm confused. Aren't we trying to determine the displacement vector?
Well, let's say you have to displace through observation. Let's say you have 3 in sequence.
But I thought this is how we're going to determine displacement.
No, this requires a displacement too.
Yeah.
Because you need the distance between the 2 points.
So this,
But that's not, that's just a, to me, the displacement is both the pose and it's not just the distance, it's the angular.
It has to be the 3D distance.
Yeah, but this is just a linear distance here. It's not 3D distance.
Oh,
Right, it's a,
Right,
it's a
right.
normal distance. I mean,
yeah, just a scalar.
scalar. So anyway, it seems like this issue, to learn the morphology of an object, it seems like you have to be able to detect these normals. You have to be able to detect the boundaries of an object, and that's really the plane, the tangential plane, and the normal is just the normal for that. So it sounds like a pretty safe technique to use, right?
Yeah. Yeah, I feel like if you can't do that, it makes things very difficult.
Yeah, I think
You
like
can't tell the curvature of a surface.
you
Or
have to be able to.
so, is this like a worthwhile idea to pursue further? Any objections or alternative ideas? Because I guess then it would be interesting to look how we could extract those normals from like a vision patch or a small sub-point cloud of a touch sensor, for example.
I was confused. Didn't you just say that if we have the point cloud, we can extract these, right? And don't we have the
Yeah.
point cloud? So
Yeah, if we have, so right now the touch sensor always just gets 1 point. Now it would need to get like several points in close proximity. And then we can get the normal from that.
yeah.
But don't, at each image patch, don't you get a whole bunch of pixels with depth?
Depends. So how I was using it before, I just get like 1 point in space.
Oh,
But
But you could, I mean, it's there, right? Isn't
I
it
could get multiple. It's
Yeah.
not, yeah.
it's
I
all
mean,
there.
yeah, the system is getting depth at every pixel.
Yeah.
No, but I think you're using the mesh directly, right? Not using the sensors.
Yeah, so right now for the cloud I just showed, I just used the mesh directly.
But doesn't the mesh have a little triangular,
yeah, there's surface. You can get the surface from it.
you have the certain, and you calculate the normal?
Yeah, so
But
that,
a real system wouldn't have access to the mesh.
Oh, well, we're getting the mesh because we're cheating habitat?
Yeah.
Yes.
No, I think.
That's what I meant. But if it's operating on the patch, our depth patch, then you have depth at every pixel.
Yeah, just take a few surrounding pixels and you capture good. Sounds doable, right? Is there any?
Yeah, yes.
No, it's just a question of knowing how much noise it can tolerate.
Well, I guess you could try, that would be something to find out, then, maybe, right, how good.
There's also the issue that was shown that if you have a plane that's nearly normal to your view, your sampling is much coarser in the Z dimension for that surface than it is for the something that's normal to you know, your however you're capturing these Z coordinates. So yeah, the mesh is, you know, is almost a ground truth there. But if you look at what you're getting as a sampled Z image, you have to be kind of careful about which points you associate nearer to each other.
I didn't follow that, Kevin. I thought that if I was looking at a plane that's normal to me, that would be an easy one. You made it sound like it would be harder. I imagine the hard one is, let's say I'm looking at I have a cube, and the cube is almost, I'm trying to look at Viviane had this last week, you know, the top of the cube was just going off at a very, very slight angle for me. And therefore you really couldn't sample many points on it. That seems like
right. You're going to get fewer samples off of that plane of the cube than you would that one that is normal to your viewing direction.
Yeah.
So what I'm saying is that when you say that I'm just going to take this cluster here and average, you know, construct a normal from the XYZs from there, you have to be a little bit careful about how you choose them, because you could be on a corner, in which case it's ambiguous, for instance.
Yeah. You know, working on this idea I'm working on, I've been thinking about things like cubes and faces and things like this. And it's really interesting when we, it's like, you know, as I look at an object and I rotate it in front of me and I'm learning that object, you know, it seems like I have this real bias towards remembering the surfaces. Like if I look at a cube and I'll remember what's on each face of the cube, but it's not like I look at the corner of the cube at a corner on towards me and say, okay, that's something I'm going to learn. It's like I don't learn that. It's like, and then I just rotate to see the next face, and I rotate to see the next face. And so like I know it's a cube, but therefore I'm not even going to try to learn the displacements looking at it from an angle. I do the same thing with like a face. Like, you know, we kind of remember a face like straight on from the side. And this is why we're really bad at drawing faces from angles, because you don't really store it that way in some ways, you know. So my point is that when we observe objects to learn it, like if I'm going to learn a cube, I will probably learn the features on one face, and when it's pretty much orthogonal to me, and then I'll rotate and learn features on another face. I won't really memorize what it looks like from a corner. It seems like I don't do that. So
but you need to at least recognize the boundaries, you know, maybe not the corners, but you need to know where the edges are just to define anything.
Yeah, well, yes. So the theory I'm working on right now is that in general, the basic way we learn displacements of features is in 2D. And yet it's this 2D displacement set of features is actually wrapped around a 3D morphological object. And so you know, it's easier to, we want to get those features into a 2D sort of presentation for us, so we can sort of do better at recognizing their relative positions to each other, not when they're really skewed and scans to us. Then we'll just rotate the object to see that. You know what I'm saying? It's like if I'm learning what's on the coffee cup and I'm rotating the coffee cup, I don't look around the edges. I look sort of what's facing me, and then I keep rotating to what's facing me, and rotating to what's facing me. So it kind of avoids this problem a bit. I don't try to imagine what's around the corner or just really skewed me. I just rotate till I see it clearly. So anyway, I think there's various ways to get around those problems.
A learned model will also capture those edge cases, Kevin. Because you're talking about heuristic averaging to get the normal, but we're thinking more of learning a system that maps like partial point cloud or sequence of image to normals. And then the learned system will be able to capture those.
Yeah, I mean, when I said you have to be careful, what I meant was in the there's going to be some context you're going to have to recognize to know how to weight those contributions from the points.
But it's a learned system.
No, I understand it can be learned. I just said it doesn't pop out of a simple analysis, you know, in a diagram. That relationship, I agree, could be learned. It's just not going to be. It's going to take some training to be able to learn that. Not so much edge cases, if you pardon the expression in the epistemological sense, but they are things that will become salient, and then you use those as anchor points to decide how to go with it. But I'm not disagreeing with you. I agree that those could be learned. It's just that it's mathematically, it's if I was to do it by hand, it's not necessarily straightforward.